because I'd like to be able to try it again next time. You know what I'm saying? Okay, advice for the day. Give up. At some point, hanging in there just makes you look like an even bigger loser. Written in the corner. All right, so today, now that Blake's here, we can start.
Oh, I see the show, Blake.
All right, today we're going to do some problems based on beam design. So, select the lightest weight steel wide flange beam from Appendix B. Everybody brought their book, right? No, I'm sorry. Everyone brought their Strength of Materials book?
Oh, no.
All right.
Wait.
Then you're going to have a tough time answering this question, I think. Oh, look at you. Yeah, except that that's not the Appendix B. I'm sorry. Clayton, you going to join me? I'm stalling for you. I'm stalling. Let's go. Stalling. All right.
I feel so great.
Did you bring your book? Did you bring your book? Seriously, nobody has their book.
How about that?
Somebody read the book. Select the lightest weight steel wide flange beam from Appendix B that will safely support the machine loading shown. So we have this picture. The allowable bending stress, or the allowable normal stress, should have said, is 24 KSI, and the allowable shear stress is 14 KSI. And there's the beam. So what do we do?
Free body?
All right, we'll do a free body.
Dang it.
We got 5 here. Okay. Reaction forces at A and B. And everything is 2 feet. And this is 5 kips. All right. Free body diagram. Now what?
We need to solve for our reaction forces.
Okay. Solve for the reaction forces.
Sum the forces in the Y, and then we'll do a sum of the moments about the A. And those are both equal to 0.
Okay. You'll let me do some of the moments? Or can you look at the picture and tell me what A and B are?
A and B, because it's symmetrical, A and B are going to be the same.
Right, because of the symmetry, we know that A and B are both going to equal 10. Okay, so we know what they are. Now what? Our designer beam.
Okay, so now we want to find where the max stress is.
What stress? Max what?
Been, normal and shear stress.
Okay. So which one do you do first?
We'll do normal first.
Right, normal first because why?
Because
What did we say last time?
wait,
Cable's off the hook, everybody else has to answer. What did we say last time? Why are we gonna do the normal stress first?
Well, that's always,
Always greater, right?
Not always greater, but it's usually, what's that? Yeah, it's driven by the fact that beams are usually fairly long. So the bending moments are typically greater than the shear forces. Right? The bending loads are typically greater, have a greater impact than the shear loads. And so we're going to start there. So remember the process is check for the bending, the normal force, the normal stress due to the bending moment first. Design around that, and then confirm at the end that your shear load is being borne without failure. Everybody with me on that?
so, okay, so I thought that makes sense. Earlier on in the course, didn't we say that things are more applicable to like to fail and shear though?
So shear is things are weaker in the shear stresses. The shear stress for failure is typically lower than the normal stress for failure, as shown up here.
Yes.
Right? But that doesn't mean that the shear stress that's actually being applied is going to be greater than the normal stress that's going to be applied. So in the context of a beam, we're most often going to have a much greater normal stress than we are shear stress.
Due to the fact that it's designed to support moments.
Because it's designed to support moments, exactly.
Okay.
Okay? Okay? So we're going to find sigma. So what do we need to find sigma?
The maximum moment.
Right. Right, it's going to be, what's the equation we're going to use?
My over I.
And so we're going to find M max, the maximum moment. Right, because Y is the same for the whole beam. It's a geometrical value, it's the dimension, it's the dimensional value.
Is that the entire height or just from the middle to the top?
It's from the neutral axis, right? Well, and I is universal for the whole, the whole beam. So Y and I are geometrical figures, so we just need to find M max. So where's M max going to occur? How do we find M max?
Could you use a moment diagram?
Shear moment diagram, right? So we have a shear moment diagram. Here, let me erase all this. Now look at those are 10. Okay, here's our shear diagram. What's the shear at the left?
0.
10, so positive or negative 10? Positive or negative 10. So we have our beam. Right, we have a force pushing up here. Oops, sorry.
Oh, but a positive shear.
So, what was that?
Well, shear positive convention is downward, so it's like it's a positive shear, but a negative force.
So, right, so that, you're saying that is
Positive.
right, it's a positive shear because it rotates it clockwise. There you go, okay. 10. All right, what do we got? Then what do I do? Where do I go from here?
Over.
Then what happens?
Down.
Okay, what's this value down here? Right, so shear wise, looks like we're going to have pretty much the same deal on both sides. Now let's do the moment. What's the moment on the left? Where am I going to start on the left side? So you start at 0. Right, it's a pin. It can't hold a moment. So it can't be a moment on the left. What about the moment on the right?
0.
Also going to be 0. Because it's, again, there's no moment, it's just a roller. So what do I do from here to here?
Add the area underneath.
Straight line up to 20? Like right here?
No, like at an angle, yeah.
So. That's what you're saying.
Yes.
Okay. Now what?
Then another line, up to 30.
For a line up to 30.
Yep.
Okay.
Then you're gonna go straight across.
Straight across.
And you're gonna go
Same pattern.
follow the same pattern. Hopefully, so.
Right. So where's my maximum? What's that max?
30.
Good? So now am I ready to calculate sigma?
Well, we need to
We
find
gotta
out.
calculate I.
But we don't know I. We're trying to find the design of the beam. Ooh.
So now we can find our S.
Right, so really what we're trying to solve for here is the design of the beam. So in some sense, we're trying to solve for I over Y. Where am I? Sigma allowed. Right? The section modulus. We're trying to find the section modulus that we're going to need to support this load. So the section modulus is M was 30. What is that? Kips, so it's kip feet. Sigma allowed is 24 KSI. And what do I do there?
From this,
Yeah, what do I do with that?
now we go to the chart, right?
Do I need to convert it?
Yeah, we have to convert something.
Multiply the 30 by 12 to get it in the cubic.
Right, so I gotta multiply that times 12 inches per foot. So I get kip inches, so that my inches and inches cancel out. That's 360 divided by 24 is 15 inches cubed. So now what? The K's cancel out.
Oh, I
This
see.
is kilopounds, and this is kilopounds per square inch.
Yeah, I see.
So kilopounds, and then we get inches cubed.
Would you want to multiply by y, by the length of the beam?
Nope,
Why is it
we don't know what the height of the
the
beam
length?
is.
Why is the height?
We don't know what the height of the beam is.
So now we want to go to our table, right?
So now we go to the table. Because these I over Y values, the section moduli, are what specifically is calculated for us. So, do we want an S that's just less than 15 or just greater than 15?
Do we want to say that again?
Do we want an S that is just less than 15 or just greater than 15?
Great.
Greater. We want a higher modulus. We want a stronger beam than the 15. So we have to find an S that's greater. Now, how are we going to choose? We've got a whole bunch of them in there. You see the S's?
And also the lightest weight.
What's that?
And that's for the lightest weight.
S for the lightest weight. How do we determine the weight of the beam? All right, so we have all these beams on there. We got a W 16 by 40 or something like this, right? Those kind of numbers. How do we find the one that's the lightest weight?
The one with the smallest volume, because they don't have the same density.
Even easier than that.
It's just the last number and the lowest number.
Right, the smallest of the second number. The second number is the pounds per foot, mass per unit length or weight per unit length, and so you want that number to be small.
So that one is 40 pounds per foot?
Right, and 16 inches high.
Why do they not give the width in that?
Why did I not give the width?
Yeah, why do they not give the width? I mean, I know they.
They give it in the table, but but typically the constraints that we care about are the height.
Yeah.
And we'll see about that in a second with the shear, the height, and then, I mean, we care about the moment of inertia, all those other things too. So what do we have? It'd be great if we could all look at a book and look it up,
If all,
100.
get on the same page.
No. Sure. That's
So
So what one do you want to go with there? Somebody make a random selection. Now, what direction are we bending? If you look in the table, okay, you guys just have to remember this, so when you go back to your table, you will. When you look in the table, there are two columns of S's and I's, one for the X and one for the Y axis. Looking at the picture, which axis are we bending it about?
X.
The X. 50-50 shot and you blew it.
We're
We're bending about the X, so we want to find the section modulus in the X direction that is at least 15 and that has the lowest amount of total weight per unit length.
It must be as close to 15 as possible.
It has to be over, at 15 or over.
So like,
Now it's more about just the length.
so then it's just, so like. Yeah,
The length is fixed, it's 10-foot long beam.
so like this one's 19, that's 15,
So what do you got?
what is the first, what's the W first number?
That's the height of the beam. It's irrelevant in this particular conversation.
I have to take a week.
And 16.
good job,
So we're going with W12 by 16.
That'd be correct. So the 12 by 16 is the lightest one that has a section modulus over 50 among the wide flange I-beams. Okay. So, are we done? Have we made our selection? Are we good?
I got a quick question. For wide flange beams, is there a specific amount of width to the flange
It's specified for each one.
for each beam? So it's not like
Right, there's not a-
wide flange doesn't mean 6 inches or 10 inches or something.
Right.
Okay.
So it's one of the tabulated values. It's the B value, the width. Yeah, so, if you look in the table, you can see the widths go from anywhere from 12 3/4 on the high end down to 4 inches on the small end. Okay? So now what do we have to do?
Verify.
Verify. So now that we've found what condition we need to meet, that we need to verify. Oh, if only I could spell. Verify tau.
So I have one other question. You said we're bending about X. I'm guessing the X-axis is coming out of board.
We're bending about X, so X is the axis coming out forward. Because Y is this direction.
Okay, so is that what we normally do when we like label? Is that just because we did our?
Well, it's just if you look in the book, again, if you had your book, you would see the cross-section, they have a cross-section of the beam. And they specify, this is the X-axis, this is the Y-axis of the beam.
Gotcha. Okay.
Okay. How do we verify tau? How do we verify the shear stress? Plug it into what?
VQ over IT.
Right. So where are we gonna, what value of V are we gonna plug in? 10, right? Again, if I verify tau max, so I can use D max. Okay, and because this particular beam, for this particular beam, Q, I, and T, we should be able to calculate from the tables. Now, there was something that was shown in the example problem, I didn't really talk about it in class. I think I may have mentioned it, but we didn't do it in a problem. It turns out that in many engineering applications, they allow you to make an approximation. Okay, so if you remember how we did the stress distribution, the shear stress distribution on the I-beam, we talked about this last time, right? It's sort of a parabolic thing that comes up from the ends, right? The shear stress here, and then in the center it does this, right? Everybody remember that? The approximation they allow you to make is to say effectively, all I care about is some average shear stress in the center. So what they allow you to do is they allow you to essentially incorporate, if I did the average shear stress, it wouldn't actually be there. It would actually be here. Because what I do when I calculate the average shear stress, I take all this area and kind of use it to fill in all of this area. Can you see what I'm saying there? Well, actually, this whole thing. But. So you take all the shear stress that's born in the flange, which is not much, and sort of fill in this web so that we end up calculating. You know, that's sort of the idea. So there's an approximation that is often allowed where we just care about V over the thickness of the web times D, the height of the web. I think it's D, the D that they use in the book, D, the height of the web. D, yeah, top to, look at the picture, is that the top to bottom dimension of the I-beam?
Yeah.
Yeah. You see what I'm saying? Because so little shear load is born in the flange that they're essentially saying, well, let's just replace this with a single web that runs the full height. And find what the average shear stress is in that. Because there's just this parabolic distribution here. If I find the average shear stress, by and large, it's going to be at or above the value of the peak shear stress.
So we've done that on our test.
Yeah. We didn't talk about that, yeah. Unless I specifically tell you. So it depends on the code. It's all driven by, building code and that kind of thing. Right? It's not something. There's some regulating body that says for this application you can use the approximate stress, or no, you have to go back and actually calculate the peak shear stress. We could do this, right? I is given for that material. Do you know what I is? For that beam?
Yeah, 1260, sorry.
103.
What is it?
103.
Exact, 103?
Yeah. Inches.
So I've got I, right? I would only need to calculate Q for that building, for that thing, and I don't think they calculate Q in there, do they? Because, so Q would depend on the top, would just be the top half. But you can calculate, knowing, it gives you the thickness of the flange, the thickness of the web, the width of the flange, the height of the web. So you can calculate your Q, your I, everything. But generally speaking, this is going to give you a more conservative, or a faster result. So it's going to be 10 KSI over, what's the thickness of the web? The width of the web here? 0.22 inches. And what is the height of the web? Even though it's nominally, where are we? 12. What is the actual D?
So from the very top to the very bottom?
Yeah, the D value that's calculated for that.
11.99.
Okay. 11.99. So it's nominally 12, but it's not exactly 12. Okay. So if I do that, I get 3.79 KSI. Actually, 10's not, it's KIPS, not KSI, sorry. These are KIPS. Okay? And so that's well below the 14, so I'm good. So I verified that indeed it is okay. And you can see how much below the 14 it is. Right, it's roughly a quarter of the allowed value when we're right at the allowed value for the normal stress.
Okay, so I guess I'm still a little confused on when we're allowed to take this assumption into consideration.
If you're told you're allowed to take that
Oh,
consumption.
so it's just purely
If the situation, whether it's the building code or the instructor on the exam or whatever, allows you to do it, okay?
So, in that problem right there, it doesn't explicitly say,
Right, so we can go through and do the analysis by hand. So let's go through, let's just go through, we got the I, let's find out what Q would be. See, let's compare them. Okay, there's the area above the neutral axis. So what's Q gonna be? Right, the sum of the pieces. How many pieces do I have? Probably do it as 2 pieces. Okay. Oh, let's break it apart right here. So, what is that value? What's the thickness of the flange from the book?
0.265.
0.265. And B, the width of the whole thing, width of the flange?
What is it? 3.990.
Okay, so this is B. This is TF. This total dimension is D. And this is TW, which we already have. Everybody got that? That make sense? Somebody hopefully is on the calculator, because we got to, I don't have these numbers in my thing here, because they didn't solve it this way. Okay, so what is Y tilde prime A prime for the top piece? What's Y tilde for the top piece? This is actually D over 2.
TF over 2, so 0.1325.
No.
Plus the height.
So it's actually going to be D over 2 minus TF over 2. Right? It's this, the
Oh, is D
centroid of that
D
piece.
the overall height?
D is the overall height,
Oh,
so
okay.
D over 2 minus TF over 2.
Gotcha.
Ever see that? Okay. We'll plug those numbers in a second. What's the area?
TF times B.
TF times B. Okay, for the second one, what is the Y tilde?
T over 2 minus TF divided by 2.
D over 2 minus TF divided by 2. And the area?
TW times D over 2 minus TF.
D over 2 minus TF times TW, right? So let's go through and figure out what those are. D over 2 is 5.995 minus TF over 2, 0.1325 times 0.265 times B, which is 3.99, plus D over 2 5.995 minus TF, 0.265, divided by 2, times 5.995 minus 0.265 times TW, which is 0.22. And we're all relying on Ben. Let's hope his calculator doesn't die because everybody else is just sitting here staring at me. Gotta work this out ahead of time, I guess. Didn't think that through. We're gonna trust that Ben does it right now. Don't screw up, Ben.
This is what I measured up.
You can do it then.
Just the check messing up.
Can you double check?
0.1325.
Actually, that's something that's kind of quick.
This is in the video.
No, it's actually not because you're off screen. You have anything, Ben? Oh no. Kayla took over.
It was too large.
It was too large?
Yeah, it's supposed to die. Supposed to touch.
So we have to have 6 times 4 is 24. The quarter is about 6. And here we have 3 times 6 is 18 divided by 5. So somewhere in the neighborhood of 10 would be right.
Yeah, well, that is right. So, yeah.
What do you got?
11.4.
9.78.
Dang it.
Let's see which one gets closer. I'm gonna go with that.
Okay. So we have 10 kips times 9.78 divided by I, which is 103, times T, which is TW, taken to the web, which is 0.22. What does that give me?
.32.
4.32. So you did a more rigorous analysis. It's actually a little bit more shear stress, but you know, so certainly within an order of magnitude, those are close. Does that make sense? I'm going to go with the 9.78. Okay. Whether it's 9.78 or not is wrong or not, I mean, there's still a ballpark at 10. Okay. Does that make sense? So, what I would do, honestly, in most cases, I would do this first, and if I'm close, I'd go down and do it more rigorous. So if you do this, you find out, yeah, I'm at 20% of total value, that's fine, go on. Okay. So in terms of,
So that's normally.
that would be the way that you could proceed through it, yeah. But on the test, you want to make sure you rationalize that.
So if on a test, if you just asked, like, the beam design, we wouldn't technically have to further on and go, but if, say, you had specifically asked for the, you know, what the Talmac, you know, how close it was, then we wouldn't have to.
Right. If I ask for the maximum shear stress, you do the real deal.
Yeah.
But if I'm asking for the beam design, you verify, yeah, this is good. You know, okay. But you would say, you know, this is well below, so this approximation indicates that it's still good enough. Yeah.
The approximation is technically over engineering it, right?
Not necessarily. It
Not-
depends on
not
the characteristics of the beam. You can see in this case, right, the actual shear stress is going to be larger than what we approximated. Okay. But the approximation is that the shear stress borne by the flange roughly is going to represent this out here. But in reality, the average came in sort of here. the average, gave us a line there, so that we're actually slightly below at the peak. Does that make sense? And that's going to depend on the characteristics of the individual peak. Okay, let's move on to another one. Let's look at that bottom one. The joists, actually, let's skip that one. We only have a little bit of time. Let's go to the top one there. What's that?
What's the choice?
Is that a
joist?
lounge
A
chair?
joist
spot?
beam.
Is that a massage chair
No, it's a piece of equipment. It's
for massaging?
It's, all right, so, determine the top one. Determine the minimum height and the minimum depth h of the beam to the nearest eighth of an inch that will safely support the loading shown. Allowable bending stress is 21 KSI. Allowable shear stress is 10 KSI. So what do we start?
Dual free body diagram.
Free body diagram. Okay. Rollers here in the center, and then we have a distributed load down here at the end. Dimensions are 12 and 6. And this value is 4 kips per foot, is that what it says?
Yep.
Okay, what do we do? What do we do?
Fine.
Can I ask a quick unrelated question?
Does it have anything to do with the piano?
Not necessarily. Well, okay, I have to ask, what is that machine in the bottom?
It's just a piece, if somebody stands, it's a side, it's a view from the side.
Well, like, what
Somebody's
is it?
thing to operate like this, I don't know.
Like a cash register and an ID?
No, it's a big, you stand up here, a person stands here,
It's a DJ.
you know? You see what I'm saying? A person stands here and operates this thing.
Just balances on an ID. That was on video.
That was on video.
All right, let's go. What do we got?
We need to find our reaction forces.
Find the reaction forces, very good.
Summation Y, summation normal dot A, correction amplitudes.
A, B, reaction forces. 4 kips per feet times 6 feet is 24 kips, right?
So A plus B equals 24.
So A plus B equals 24, and 12B minus, what, 15 times 24 equals 0, right? So B, oops, I don't feel like it's the right problem.
Wait.
What's that?
um,
What? I'm not sure. It's
15.
This 24 is going to be applied in the center, which is 15 feet from A.
Gotcha, yep. It is 15.
Okay? So that gives us B equals 30, I think. Yep, B equals 30. So A is equal to minus 6. Yes?
Quick question.
If we're actually building a construct, why would anyone want to use a pin joint and a little roller? Why wouldn't people just use pin joints? Do we just have that to illustrate a point in the book, or is that an actual
No,
common?
you always, no, simple beams always have to have a roller at one end because of thermal expansion or any other kind of physical dimension, right? If it's pinned at both ends, then you're rigidly holding it there, and it wants to expand thermally, it has to go someplace. You're gonna create internal stresses. If it's on a roller, you don't create any internal stresses. Okay, so we have pulling down here of 6 kips, and the force pushing up there of 30. All right, now what? What's that? Shared moment diagram. What do I start out with? Shear on the left. What's that? -6, right? Because, again, this is down, so this has to be up, right? Which is turning it counterclockwise. So -6. Okay, what does it say? What does it do from there?
It jumps up. Oh, it goes straight over, yeah, that's well.
Straight over to there. Okay, then what's it do? Up by what?
532.
Up to 24, right? And then from there,
Linear way down to 0.
down to 0, right? Moment diagram. Moment at the left, 0, starts out at 0, because there's nothing to support a moment. What do I do from there?
Linearly increase to, linearly decrease to 6 times 12, which is 60, 70, right?
72. -72, apologize to those of you on video who can't see what I'm writing. Okay, -72, then what? Then what?
Then it's parabolically increases back at.
Parabolically concave up or concave down?
Concave up. Because there's greater area, the.
The greater change,
Oh, yes.
right? All right, so V equals the derivative of a greater positive slope here than I have there. Okay, back to 0. All right. So, now what?
So now we need to find the maximum, which is, say,
-72, right? That's kip feet. So now what do I do? Should I just start writing? 6 minutes. S, right? I'm gonna solve for S.
negative.
72 kip feet divided by 21 KSI. Again, gotta multiply by 12 inches per foot. What's that give me? They didn't give me the value. What is that? 7, 4, so we got 2 7s times 4. What is it? 41.4 maybe?
41.14.
41.14. That's my S. Okay, what does that tell me? To go to the table. No. What kind of a beam is it? What kind of a beam? What shape beam is it?
Looks just a bar.
It is. It's just a bar. The cross section of that beam this. I didn't say it was a wide flange beam, I didn't say it was a channel beam, what's that?
It says it has a uniform thickness.
Oh, uniform
Yeah.
thickness, right, 3 inches. Right, that's what it is.
And you were able to get that from the 41.14?
No,
Oh,
from the thing over here.
Okay.
And the problem says it has a uniform thickness of 3 inches, and it shows that it's a beam, it shows that there's no lip or anything, right? So, how do I get from 41.14 to defining H?
No, we can, well, we can find our, moment of inertia.
Right. This is equal to I over Y.
You can just find what?
And we're solving for Y, but I's can have Y in it as well.
Mm,
So what's the moment of inertia for this thing? Again, about the x-axis.
1/12 times, 3 times the height cubed to the 4th cubed.
Cubed. Okay, so that's equal to h cubed over 4, right? So this is h cubed over 4 divided by h, so that's h squared over 4. Oh, no, yeah, sorry. H over 2. Right, h over 2 is y, measured relative to new flux. Okay, h squared over 2, so h squared equals 82.28, so h is equal to 9.07 inches. All right, am I done?
Verify,
Verify.
testify.
Now we gotta verify tau. So, what method of verification do I want to use for tau? Do I want to use the approximation, or do I want to use the actual deal?
Say that we use the approximation method,
No.
so we should probably use the.
Yeah, because this is not a wide flange beam, right? The whole deal with the approximation is we have these wide flanges, right? So the shear stress kind of ramps up in the wide flange so that in the web, the shear stress distribution is not very greatly, right? It's not really a full parabola, it's just kind of a parabola on a square, you know what I'm talking about? Here, in this case, I'm getting a full parabola. Because I don't have flanges at the top to offset my starting point for my shear stress. So I can't use that approximation here. I have to go back and use tau is equal to V Q over I T. I've got I, h cubed over 4. So now I've got to find Q. What's Q going to be?
Or of that top section, so the distance in the center of the top section,
Which is?
h over 2.
Nope. Almost.
H plus h over 2.
H over 4. Right. This is already h over 2. So this is going to be h over 4. So h over 4 times, what's the area?
H over 2.
Right, times 3 times h over 2. So that's going to be 3h squared over 8. What's t? Which is 3. So now I can plug this back in. So I've got my v. What's my v? Close. 24 times 3 h squared over 8 divided by I, which is h cubed over 4 times t, which is 3. So the 3's cancel out. I got the h squareds cancel out with h over 4, so that becomes 3. So I've got 3 over h over 4, that's 12 over h, and kips per square inch, everything else is in inches. So it's 12 over 9.07, so 1.315 KSI. Does that make sense? Okay, so I had to use the full value here because it was not a wide flange beam. But otherwise, much more straight. And the nice thing about it is wide flange beam, the reason it's so helpful in the wide flange beam is because it's much more complicated to calculate Q for those things because the values are not even, not uniform. So,
What's the real world application of a wide flange beam? Wouldn't just a regular bar be stronger? Is it because you reduce the weight?
yeah, it's completely about reducing the weight and therefore the cost of the.
But you still get almost as much strength. Or?
You get a lot more strength. You get tremendous amount of great strength out of a solid beam. You had a beam that was 4 feet 4 inches wide and what was the other one, 12 inches high. It'd be enormously strong. It'd be incredibly heavy,
Right.
and incredibly expensive to manufacture as well. So you'd much rather have the I-beam, which is a fraction of the mass and cost, and yet still has a pretty significant proportion of the total bending stress. Now torsionally, that's going to be different. The torsion strength of an I-beam is a little different. It's a lot more complex to do that, so you have to go, it's kind of another level mechanics torsion in an I-beam.
So I was wondering, why you would want to use that for, those big pillars that they put in the ground. I mean, cost is one reason, but is the amount of strength compared to the weight that's pulling down, so